in this, go back to this Vapni block diagram, put all probability distributions that we will need in order for us to do the following. For every prediction that we are going to get out of our machine, that prediction should have some form of uncertainty. So all the previous discussions we have done up to now in the regression problem, we were getting a price, let's say, of a house or any kind of real number in our y-hats. Now we will have not only just the price of the house, but also we have an uncertainty of how uncertain our predictions are. So most of these machines that are to be useful, they need to have that uncertainty output. It's quite different to say I'm certain 100% that the house price of that house will be 350,000, but quite different if you say that, yeah, there will be 350,000, but I'm going to add to it plus or minus 100,000 into that kind of price. So that we will see also in classification, and that's why we start now in treating learning as a probabilistic problem. So we have seen in this kind of block diagram that we have a data generator. This data generator now will be decorated with a marginal probability distribution we'll be calling P of X. So this X over here is a sample out of this generative probability distribution P of X. And that X will actually go through the target function, which is again unknown, and it will produce at the output the target variable Y. And probabilistically, we can express this Y as being obtained out of another probability distribution, which we will start calling now P data. So let me just change that to be the so-called P data of X, and actually draw a little bit this box differently to have some kind of space. So this is now P data of X, and this probability distribution will be the P data of Y given X. So this, I mean, the qualifier data over there on the probability distribution is actually done for a reason, and we have adopted the Ian Goodfellow's kind of book notation for all the probability distributions we'll code here. So the sampler now sees both of these X's and Y's, and in fact what we can actually tell here is that the sampler will sample out of a joint probability distribution P data of X comma Y, which is nothing else, as we have seen in the probability review section, as the product of P data of Y given X times P data of X. Now everything is kind of consistent here in terms of the product rule, and it will the sampler will sample out of this joint probability distribution and give us some examples. And if we are to describe probabilistically that kind of sampling process, we went from P data of X comma Y, and over here we can associate the so-called empirical probability distribution of P data hat of X comma Y. And this is kind of the histogram, if you like, if you want to think about it, of all the examples that the sampler gave us out of this P data hat. Okay, so that's a very important probability distribution, because that's what is coming, is involved in the input of our machine. And going back to this machine kind of block diagram, we have specified the hypothesis set. The hypothesis set was offering to us the hypothesis, which called G of X comma W. The Xn obviously was associated with our data X, and W was a vector that was encompassing all of the parameters of our hypothesis, and we have seen several of those hypotheses in the sinusoidal regression problem. We had the objective loss function, and we had the optimization algorithm, which is the stochastic gradient descent. And finally, we had this final hypothesis at the produced at the output of this optimization procedure. Now, instead of actually producing now a function, g, that it was claimed to be as close as possible to the target function f, that was our attempt to make it as close as possible to the underlying target function f. Now we are going to be producing a probability distribution called p-model as our hypothesis. So our hypothesis will actually be also probabilistic in nature, so it will be p-model, and this p-model will have again it's going to be a function of x, and will have a set of parameters w. In fact, it's going to be conditional. It will be y given x comma w. And the reason actually this y given x comma w is we want to match that to as close as possible to the sort of underlying probability distribution of our labels. We are trying to guess labels, the labels y, and we are going to offer a probabilistic model for that kind of guess, for that kind of hypothesis. So therefore we will have a parametric version of that p data. Evidently the p data is not available to us, so therefore we have a parametric version of trying to approximate the empirical probability distribution p data hat. Okay. And so we will see now how this p data hat and p model can come closer to each other in a similar fashion as we have seen in the so-called deterministic equivalent discussion we had in the regression problem. And the other thing, of course, we need to convert this discussion to convert from a deterministic discussion to a probabilistic discussion. We have to change this kind of loss function from something which is a function to another function which will include the p model and p data hat. And if you remember, we introduced the equivalent function that we called KL divergence or relative entropy just in an earlier video. So we will be start now calling this cross entropy, and we'll symbolize with capital C and capital E cross entropy. And this cross entropy will have two things as parameters, the ground truth and the y hat, in a similar way that the mean squarer also had these two parameters as arguments, the predictions and our ground truth. And we'll see now how this cross entropy will be derived out of relative entropy for a specific problem that we will pose. In fact, this cross entropy will be the maximum, or related to the maximum likelihood. So we'll introduce now maximum likelihood is probably one of the main lessons in this specific sort of module that we are discussing, and we will do that next using a simple data set. So we'll be introducing now maximum likelihood using a simple case where for the moment we will be ignoring our labels y. There will be no labels in this problem. In other words, so what I'm doing right now is I'm actually giving you some kind of data set that it is consists of real numbers. This is just x's on scalar numbers on the real line. Let's call them the so-called x1, x2, all the way, let's say, to xm. M real numbers on the real line. And I'm asking you the following question. This question is going to be quoted over here at the top. So the question is, what is the model that fits the data? or maybe I can just write it as specify a model that fits the data. Okay, so that's a kind of a reasonable question. It comes to various forms. In practice, you probably have seen it as earlier as potentially kind of a density estimation, kind of histogram plotting, and sort of so many other questions that are associated with this question that we wrote over here. And so the data set is going to be evidently as going to be denoted by let's say x1 xm. Note the kind of strange kind of x there is there in order for us to sort of not to associate it. This is not a vector, that's basically a set. So the set consists of all the data that we have. And according to the Vapning kind of block diagram, the very first thing that we have to do, if I actually go back to this kind of block diagram, we will see that we don't have now labels, we have just x's. So there is an underlying generative kind of distribution p data of x that it is sampled from the sampler. The sampler is giving us some x's, m x's that I just drew. And we have now as input just the x's, and the first thing that we have to do is after we have now introduced the probabilistic version of the Vapning block diagram is to suggest a suitable p model, a suitable probability distribution for this kind of x's. So if I go back to this kind of diagram, we have now, we need to write now this kind of form of this p model. I will suggest out of many probability distributions all that are appropriate for the problem, and this problem is because x's are in the real line. We were looking to find a probability distribution which is for continuous random variables. And so one of them is, you probably guessed it, the Gaussian distribution or the normal distribution. We have emphasized on that distribution in the probability review. So let's write down our hypothesis. So our hypothesis for our, in other words, p model is that is evidently going now to be, there are no labels, so the p model is going to be just the x comma w, and x is not even a higher dimension, so it is just a scalar, so there's no underline here, but it could be, of course, we need to put underline the around w, under the w, because it's a set of parameters. It's going to be the normal distribution of x given w. We can write this. So given a set of parameters, and in many instances, actually, we can write this as a conditional given w. Okay, right. So we have now, you probably know the functional form of that is 1 over square root of 2 pi sigma squared times e of minus x minus mu squared divided by 2 sigma squared. So that will actually be the our p model. And the set of parameters here, as you can actually see, is the vector w, that corresponds to the mean and the variance of this Gaussian distribution. We have 2 parameters in this kind of problem. And the moment we actually wrote down the functional form of our probability distribution, that we believe that it is the best, the most suitable one for describing the data, we converted this kind of question. That question now evolved into the following question. So I will just write it as q prime now. This question is the following: what are the parameters of the p model that fit the data? So I might just draw this Gaussian distribution over here, Okay, so that's my P model. I assume this is going to be Gaussian. That's a nice bell-shaped kind of curve, and we can actually define the specific parameters that are present, right, in drawing this distribution. This distribution has a specific mean and a specific variance, and for that specific mean and variance, it is located over here and has this kind of uncertainty built into it as a probability distribution. Okay, so now we have the this kind of following question. The question becomes, what is how we are going to find these parameters. So we have now effectively a parameter search problem. We are now trying to try many parameters, just like what we have seen in the sinusoidal regression problem. We were changing the W and then the length of the vector W, and we come up with a final hypothesis. So now in a very similar way, we have to change the parameters of the Gaussian distribution in order for us to provide a good fit to the data. And as you can actually see here, this specific hypothesis with this mean, let's say mu0 over here, is really far away from the data. So it makes sense for us to have the following evolution of our question. If we are to follow the same principle as we have done earlier, in other words, to convert this parameter estimation problem into optimization solution problem, then it's actually reasonable to write now this question as follows. So what is the objective function? Behind every optimization problem, there must be an objective function. Of the optimization problem. Of the optimization problem that will result, will give us a good, in quotes, choice of the parameters W. I will call this choice W star of the P model. Okay, so these are the two subsequent questions, and now we will need to address this last one. So we went from Q to Q prime to Q double prime. That's our final kind of question that we need to now address. And we'll do that by introducing that kind of objective function that makes kind of some intuitive sense. So I'll now make a following kind of assumption, which is kind of essential on that the data are IID. This is a very common assumption. You will see that this expression in many kind of statistics textbooks. And IID stands for independent and identically distributed. So independent and identically distributed means that the data, subsequent samples out of this underlying probability distribution, again, we do not know the P data hat, the one that we that generated this kind of data, and in fact, this P data hat probably will be some kind of probability distribution in this kind of neighborhood of where the data are. The data, in other words, were generated independently from each other, subsequent samples. So that's the independent. And the identically distributed means that all the data came from one probability distribution. We do not know its shape and form. The only thing, of course, we have at our disposal is our P model, and that we have to provide as a hypothesis. And now we'll need to define this kind of objective function after we make this kind of distribution. The P model, however, the moment we have lots of data, can be written as follows. We can actually write the P model the moment we have someone is giving us all this kind of data, will be the probability of generating this kind of set of samples given our W. And this is a function that we will call likelihood function. So it's actually it's a function because this is only a function of the parameters vector W, only of the set of parameters W, and describes how well the data x1 to xm are, let's say, captured. Very informal discussion at this point with such hypothesis. So the likelihood function is end up being a function of only the W, as we want in any case from our objective function, and it is grounded. So it is grounded by the hypothesis. And I think we should have now some discussion as to why this is kind of an important sentence. Because the likelihood function should not be confused with something that can provide to us an estimate of a probability of any of these kind of samples. Evidently, the probability of observing sample x2 is 0, because x is a continuous random variable. And if you go back to that discussion we had in the probability review section, that's definitely a probability of 0. We have an infinite, in other words, possibilities of generating any of these real numbers x1 to xm, and therefore the corresponding probability is 0. However, the likelihood is not a probability. The likelihood function is actually capturing how likely that sample is to come from a probability distribution we call here a p-model. So let's see that how this function can be written, and then we'll make some discussion about the likelihood of each one of those samples. So we made an assumption that the data are independent, and if you go back to the discussion we had about the product rule, then you can realize that we can now write this p-model, which is effectively the p-model of x1 to xm given W, as the product of x1 given W, because of the independence assumption, times the product of p-model of x2 given W, and so on. And this product then, I think it's worthwhile spending some time to each one of those terms. Each one of those terms can be completely evaluated, and it's very easy to see how it can be completely evaluated. We know x1, so we can plug it in here. We have assumed a specific hypothesis. In this specific case, it is mu0 and sigma 0 squared, so we can plug mu0 and sigma 0 squared over here. And so each of these is a number, is a floating point number. It's a number that is going to give us how likely each data point is with respect to this specific p-model. And as you can actually all recognize, if we have a specific hypothesis located over here, this likelihood that this x1 came out of this, was generated out of this probability distribution, is a very, very small number, because it's really far away from it and the left tail of it. And the same goes with x2, and the same goes for all of the samples in this specific case. So let me just write over here that each one of them, of the terms, can be evaluated to a number. So it's going to be some very low number, like say 10 to the minus 100 for x1, maybe 10 to the minus 98 for x2, and 10 to the minus 60 for xm over here. And as you can actually see, if we start moving this probability distribution around, and probably we'll see how this probability distribution can be moved to the right direction, which is left in this figure, then we can actually start seeing how this function start to increase. So we have certain hopes to make this function that we call likelihood function our objective function. So to continue, let's write now ML continue. Let's write down the P model again, the likelihood function. I will call this likelihood function calligraphic L. The calligraphic L was also a letter that it was used to describe the loss function. So we'll see now when we move a bit forward that there is a sort of connection between the two. This is going to be just the likelihood at this point. Likelihood function. And again, function is a function of parameters. The parameters W. And the moment we have a specific hypothesis, we can write it as a P model as a product. As a product. We've seen this product from, let's say, from I is equal to 1 to M, the P model of Xi given W. And as we saw, each one of these could be a very, very low number. And what we need to do now next is to discuss a little bit about who is going to compute it. Evidently, a computer is going to compute it for us in order for us to start optimizing it. In other words, trying to find the optimal set of parameters that will maximize it. And we saw that the maximization is going to be happening probably by moving it in the right direction. So someone has to tell us where to move it. So shall we move it to the right here, or shall we move it to the left? And evidently the good direction for us is the left direction over here. So we'll bring it closer to the data. That's one thing. And the second, the computer probably, if it starts calculating this kind of small numbers, 10 to the minus 100, 10 to the minus 90, and 10 to the minus 80, then we'll go into an underflow very, very quickly for large data sets or even small data sets in this kind of case. So what we do is we do all the calculations in the log domain. So we will be, from now on, discussing about the log likelihood. So the log likelihood function is evidently going to be provided to us very easily from the likelihood function if we use the formula log of AB is equal to log of A plus log of B, which is hopefully known to everyone. So instead of a product, we will be getting a sum. So instead of a product over here, we will be having the P model. It's going to be, I'll be using the natural log, so I can just write it over here with natural log, but in general it will be the any log with any base. And I'm using the sort of natural logs over here because we have a Gaussian, and the Gaussian have exponents, and therefore the natural log is going to be a result into something which is kind of easy for us to absorb. All right, so it's going to be summation from I is equal to 1 to M of the ln of the P model of Xi given W. And if you do the math, and if you do all this kind of replacement and put a natural log in front of every of these kind of terms, you will come to the same to the following closed form expression about log likelihood. So I can actually write here that the log likelihood of the parameters w, it's a function of the parameters w, it is minus 1 over, in this specific case of the P model, 2 sigma 0 squared summation, summation, let's say from I is equal to 1, I is equal to 1 to m of xi minus mu squared minus m over 2 ln sigma squared minus m over 2 ln of 2 pi. So this is the closed form expression about log likelihood. And I understand that this is a kind of a complicated expression, and that's why I think it's worthwhile plotting it. And we have a notebook that we will go through that plots, if you like, this log likelihood. And the only thing I want to mention now before kind of plotting it is that in many of the optimization algorithms that we will be using, a descent type of algorithms. They are minimizers. So instead of maximizing this log likelihood, which evidently is going to be resulting into parameters which are close in this area, we are going to be minimizing its negative. It's exactly equivalent. So we will be, so let me write this down. So instead of maximizing the log likelihood of W, and we can actually are entitled, if I may say so, to sort of use the log in front of the likelihood function. It will result in exactly the same parameter vector W, because the log is a monotonic function. So instead of maximizing the log likelihood of W, we will be minimizing the negative log likelihood that we will be calling NLL, and symbolize it like this, NLL, with no calligraphic source. Okay, the negative log likelihood. Okay, so that's the shape of that will actually be as follows. It will be a nice, a very well behaving function in this case, because we see that we are going to have some convexity in our function. So we were hoping to have the negative log likelihood function over just one of the parameters. So if I obviously want to plot this, I have two parameters, so I need a three-dimensional kind of plot. But if I just set this sigma squared to something, to some kind of constant number, then I have and plot it as a function of only the mean, then I will get something that it will look something like that. Okay, so the sort of negative log likelihood function is going to be well behaving in this case. So we will be minimizing it. We will try with some kind of algorithm to find the minimum. That minimum we will be calling nu star. Well, of course, we'll repeat exactly the same exercise with sigma squared. In fact, the two parameters have to be jointly optimized, and therefore we will be, by minimizing the negative log likelihood, we will get the optimal set of parameters. W star is equal to nu star and sigma star squared. So this is effectively what is going to happen now is we're going to be using exactly the same optimization algorithm, the stochastic gradient descent. Stochastic gradient descent will move with small steps and will position our P model very close to the data. So it will find for us the specific mu star and the specific parameter sigma star squared. And in fact, we will see that now we're talking about a distribution of the so-called P model. And this distribution should be very close to the unknown to us, P data hat. And this P data hat distribution is going to be effectively connect these two distributions with what we have discussed earlier as relative entropy. So we will be minimizing the probabilistic distance by this kind of approach between P model and P data hat. So let me just write it down. So the negative log likelihood will need to be connected to relative entropy. Also known as KL divergence. KL divergence and relative entropy is one and the same thing. So let's try to make this kind of connection and ultimately also connect also with the cross entropy, because we said cross entropy is going to be our final destination in terms of loss. We need to do some kind of manipulation in order to go from the negative log likelihood to relative entropy and then to cross entropy. That's what we'll do next. In our side, we actually see the kind of equation version of what we have just gone through. And we started with a set of samples on the real line, and we posed this as an optimization problem. This optimization problem is shown here as the optimal set of parameters W that will result out of the argmax operator over all set of parameters W of the P model of our set of samples that someone gave us given the set of parameters W that we have assumed in our hypothesis. And we worked in the log domain as we discussed, converted that into objective function into a sum. And we have seen that we have actually reached this point, and we have replaced with P model with a Gaussian P model, and we have reached this point where we have now a negative log likelihood that we need to optimize. And in fact, this negative log likelihood can be written very generically as the expectation. So instead of a sample mean, we have an expectation over all of our samples X that someone gave us out of this P data hat distribution. So the next step in our sort of journey around maximum likelihood is to connect that objective function, the negative log likelihood objective function, with the KL divergence. So this is the definition that we have seen earlier regarding KL divergence. So let's write it down. So we've seen that, let's see, W NLL is minus it's actually argmean over all set of parameters W of a quantity that it is actually minus the expectation over all sets of numbers that can be produced out of my P data hat distribution log of a P model X given W. So this was the discussion we just had, and now we are going to borrow the definition of KL divergence from the relative entropy discussion. This is just purely definition, but now instead of P and Q distributions, we are going to plug in the corresponding distributions involved in the Vapnik block diagram. So this is the notation of KL divergence of two distributions, P data hat and P model, that we saw that are involved in our learning process. And by definition, KL divergence is the expectation over X distributed according to the P data hat distribution of log of P data hat of X minus log of my P model of X given W. This is by definition. And so actually we can observe if we are to write in other words, our objective function as a in terms of KL divergence, we note that only the second term involves our set of parameters W. So the first term, this term over here, is independent of the model, and therefore we can see that the negative log likelihood minimization problem and this KL divergence can be immediately connected. So we can actually see that minimizing KL divergence effectively minimizes also identically the negative log likelihood, because KL divergence, if you ignore this term, is identical to the expression we got with the minimization problem where we posed to find the optimal set of parameters W. So this is what we call earlier also a W star. Let me also call it W star here, the outcome of this minimization. Okay, so because KL of P data hat P model is expected value of X P data hat of minus of the log of the P model of X given W. Okay, so that's one thing. And now what we need to do is to introduce a new definition that we call cross entropy. And this cross entropy is going to be ultimately connected to the KL divergence or relative entropy by definition, and without making any assumptions, and therefore it will be ultimately connected to the problem of minimizing the negative log likelihood function. So the cross entropy that is going to be is the joint entropy, will be symbolized by CE, and it will be the joint the entropy of the joint distribution, the joint entropy of P data hat and P model. We use our distributions that we have, they are involved in the learning process, and this is going to be evidently according to this definition to the KL of the P data hat P model plus the entropy of the marginal distribution P data hat. This is the definition of cross entropy. So the given that this term now is independent for our supervised learning problem and constant, given the fact that we have been given a set of data points x, so this is now constant. We can conclude that the only thing that the cross entropy in our specific supervised learning problem, this is a very big star over here, where star is that for supervised, well, I don't want to say supervised learning because we don't see any, we don't have any labels at this point, but we will call that a bit, call out this fact a bit later for our problem, our learning problem, that is. Only this is equivalent to KL divergence. So either we optimize cross entropy given the data that someone is giving us and the fact that we don't have any uncertainty on those data because they are given, that this we don't have any dependency on parameters or any of that sort. So this is our KL divergence is equivalent to cross entropy. So from now on, we'll be calling the loss function the objective function, that is. So from now on, our marginal objective, I will call it the marginal maximum likelihood, or minimum negative log likelihood, objective is going to be equivalent to cross entropy. And we'll be symbolizing cross entropy since in this specific problem we'll be symbolizing it without any labels, so we'll just leave it as such, the cross entropy of P data hat and P model. So for now we will just call it as cross entropy of W, because we know that only one, this is a function of only the parameters W. Later, when we introduce back our labels, then we will be calling it cross entropy of Y hat comma Y. But for now, we can just leave it as such. And therefore, we hope that by minimizing it, we will be, so this minimization of the cross entropy, in other words, the minimization of the distance between P data hat and P model, is an intuitively now understood sort of concept, and now we will, the time it has come to actually see some summary in terms of the notebook we actually have built over here, and this notebook can be seen on our kind of course site following this kind of discussion. So we have some data that someone is actually giving us. This is the data that we have that someone is giving us. Evidently, these are shown as integer numbers, but can be floating point numbers. And we have now two different P models plotted here, Gaussian P models. We need to select which one makes sense for us, for the data that someone gave us. And we will be doing that by calculating, as we have done earlier, the log likelihood of the data that was given. So we have two hypotheses, mu1 and mu2. Correspondingly, mu1 and sigma 1 squared, or standard deviation sigma 1, and mu2 and sigma 2 squared, or standard deviation sigma 2. So for each of these two standard deviations, we actually can go ahead and calculate the log likelihood, which is evidently will be that summation we have seen earlier over the set of samples, the M samples that someone gave us. So we can actually see the two hypotheses, and we can actually produce the log likelihood. We can actually select the maximum or we can equivalently select the minimum of the negative log likelihood. So in this case, we don't calculate the negative log likelihood, but just the log likelihood, and evidently the hypothesis that corresponds to minus 33.30 corresponds to the hypothesis of mean 7, standard deviation of 3. So this one will be the maximum log likelihood, and that's going to be the better hypothesis out of the two. So remember, we only offered here 2 hypotheses, and we just need to select one of the 2. So what we have done here is we have plotted this negative log likelihood function as a function of only the mean by keeping the standard deviation or variance constant. And actually we can see the form that we have plotted earlier regarding our shape and form of this convex negative log likelihood function. So we can actually see that it's very straightforward in this specific problem, of course, to minimize it, and therefore we will need to come up with an algorithm that is not going to be other than the stochastic gradient descent again, that will minimize our function. So we'll see that in a sort of a complete notebook when we are facing again now the regression problem. Now we need to go into this same discussion again, but in this time we will introduce labels, and so we'll see how this objective function which is called conditional maximum likelihood turns out to be. In terms of pure equation of the loss function for conditional models, everything we have discussed on marginal models applies equally to conditional models. And the conditional models, we have a probability distribution of our p model of y given x. So therefore, all we need to do is go to the very last expression we had about either cross entropy or negative log likelihood and replace the p model of x given y with a p model of y given x and w. And in this way, we actually arrived in exactly the same equation. And all we need to do now is minimize the cross entropy for the conditional maximum likelihood. So this way, we will, adopting that kind of formula, we can actually go ahead and solve the regression problem and not only present, as we said in the very beginning, prediction, a y hat, but that prediction also comes together with the confidence that we have about it, which is essential to any prediction machine. So we'll do that for the regression problem, and then we will meet again when we have a very, very important diagram to describe, which captures the essence of the regression setting with the probability distributions present. So earlier we have seen the sinusoidal data set of someone's giving us a number m of examples that describe the relationship between x and y. And what we have actually done is that we had come up with sort of a hypothesis function g that will allow us to make predictions. So before, what we had is we had some kind of an x0 over here, or let me call this x nu, that we have never seen before. And using, if you like, the final hypothesis, we were able to determine a y hat nu. So this y hat is evidently a floating point number, a real number, let's say price of the house. And it was, no uncertainty was actually possible there to report as far as this prediction is concerned. Now with a new probabilistic kind of setting, something interesting is happening. We need to, instead of a hypothesis that will be a function, we'll have a hypothesis that will be a probability distribution. And this hypothesis will be the corresponding p model, which is going to be the conditional p model of x, w. And this, for this specific example, we'll be using a normal distribution. This normal distribution is going to obviously has a mean and a variance. So I'm going to just quote here the normal distribution where we have the y given x, comma, and as w, we're going to have here a mean. That mean is going to be some, let me write it below it so we have a bit more space. So it will be normal of y given x, comma. The w is going to be g of x, comma w. And then I'm going to have some variance that will actually capture the uncertainty. So what we have now with this kind of P model, we have the conditional mean. So write it down that the conditional mean of our P model captures the regression function. What we have seen earlier, this regression function or hypothesis was the x, comma w, and in fact, what I can actually do here to avoid any kind of confusion, I can call this w theta to avoid any confusion between the parameters of our P model, the probabilistic model, and the parameters that get to define the shape and form of this function. So this was our now g of x, comma w, which is our final hypothesis. So therefore, I can define it as kind of a w star. And evidently, this came out of some optimization procedure, which is going to be the stochastic gradient descent. And this g of x, comma w star is going to be now our conditional mean. I call it conditional mean because it is the mean of a conditional probability distribution. So if I am to plot this conditional probability distribution, if I give you an x nu and I ask you to make a prediction, well, this conditional probability distribution will be some kind of Gaussian that will be centered around this mean. So this will be the mean of the conditional of the normal model here, the Gaussian model. And there will be some kind of a variance, which I call it here as kind of sigma squared, to capture the inherent variability of my data. So here I just plotted for, a few x's represent my data set, but definitely the data set is could potentially be far more uncertain than the one I just drew. And that sigma square will actually capture the inherent variability of y of my ground truth labels. So my ground truth labels are sort of described with this variance. So the parameters theta of the P model capture the only uncertain thing that it is over here in any conditional probability distribution, which is the y. So because everything after the given symbol is given, therefore it's not random. So theta captures the uncertainty, the mean and the uncertainty and the variance of this Gaussian model for my labels. And that's why the Gaussian distribution is not over the x-axis as it was before when we had been discussing the marginal problem, but it is now flipped and along the y-axis in any conditional probabilistic model. So I think this is a very, very important kind of diagram, and is actually also shown here in your site. There are some kind of notational kind of differences, but that's the essence. We have some kind of a data. The examples that someone gave us carry some kind of uncertainty over the y axis. And for a given value of x, we call it x nu, we have a probability, a P model that will describe the conditional probability distribution. That's a Gaussian P model, as you can see here, whose mean is right on top of this regression function. The regression function itself is a function that will involve, again, some form of features it's a parameterized function over the set of parameters W that we have seen earlier in the deterministic version of this problem. And here it is kind of shown as this kind of conditional mean. And now we are able to do predictions. We are going to be able to do predictions by reporting the mean, which is going to be our estimate of the house price, let's say 350,000. But also we can report a confidence interval that it will be driven obviously by that variance of this Gaussian distribution, let's say plus or minus $50,000. Okay, that's basically the essence of the conditional model of the that is present in the regression setting. And we'll see again now soon the equivalent model for the classification setting in the next video. It's also worth noting here that all of the parameters that we see that are required for us to actually go and optimize the parameters, both the all of the theta parameters. So the theta parameter is evidently the parameters of our P model that includes the mean and the variance. All of these parameters have to be optimized by a stochastic gradient descent. So the stochastic gradient descent, instead of just coming up with values W, that the so-called W stars that will plot the mean, it also has to come up with an optimal variance that it will determine that kind of uncertainty.